first presentation, control platform using silicon carbide MOSFETs and CAN bus protocol. When the team is going, if you're the next team, if you can kind of line up on the side to kind of allow a smooth transition, and I'll kind of keep track of the time to make sure that people are staying on target. After 3 minutes, you'll see me stand up. When I stand up, that means the 3 minutes are done. So if it goes beyond like 5 minutes, there's going to be a stick or something for me to pull you off.
Good afternoon, everyone. My name is Carlos Rodriguez, and this is my group. Eating Luo, Pipu Joes, and Nick Bresson, who are part of the hardware team, software team. And Gil Rettiger and myself, we are part of the hardware team. The name of our project is Control Platform using Silicon Carbide MOSFETs and Campus Protocol. The project consisted of building a proof of concept that would show the feasibility of having one single PC GUI controlling an array of motor control systems. Now, in addition to this, our sponsor Micropipe wanted us to address 2 main problems. The first problem was the inefficient USB product communication between microcontroller and microcontroller. And the second thing was the limited operational capabilities of silicon MOSFETs at high temperatures, high voltages, and high radiation applications. In order to overcome these 2 problems, instead of using silicon MOSFETs, we use silicon carbide MOSFETs, which are capable of handling such harsh environments. And the second thing we did, instead of using USB protocol, we use a campus protocol, which allows the efficient communication between multiple microprocessors. Now, let me show you how we approach this. As you can see from this block diagram, we have a PC block on that side. That PC block represents a LabVIEW interface where the user will be able to control the motor. And we have a picture of that in figure 2. You can see that we have separate controls for the master and the slave system. And we have scrolling bars and switches to control the direction and the speed of the motor. Now, if we go back to the PC block, to the block diagram, you can see that the PC is directly connected to a master system. This master system contains a microcontroller, an H-bridge driving circuit built of silicon carbide MOSFETs, a physical motor, and some sensors. The way it works is that H-bridge, the microcontroller sends PWM signals to the H-bridge. Then the H-bridge controls the motor, and finally, coming from the sensors, we have some information going back into the microcontroller for better stability and control of the system. On the other hand, we have the slave system, which is directly connected to the master system via CAN bus. This system, instead of having a physical running motor, we implemented a system that receives an RPM and direction signal, and it displays it on the LCD screen. This proves that the system can effectively receive the information. Now, we also needed to prove that it could send back information to the master. So we take this RPM, we multiply it times 2 to imitate some type of processing of the information, and then we take it to the master system, we return it to the master system, and display it in the LCD screen of that master system. To finalize, we gained a lot of knowledge in silicon carbide MOSFETs and campus protocol, and this was of particular interest to our sponsor Micropipe. Therefore, we will document this information, and we will give it to them so that they can use it in future products. With this, I finalize my presentation. I'm open for questions.
Question?
Yes.
All right, you go first.
How much power does your overall system take?
So we're using a 12 volt supply for our H-bridge. So there's 12 volts going through the motor, and then we're using a 5 volt supply for our current sensors and our temperature sensors. Yes.
Are the microcontrollers